Please give them a warm welcome.
Thank you. I'm really surprised that there actually are people left. 5:30 Thursday, 3-day conference. I was afraid it would be 0, but I'm really happy you guys are here, and girls. We'll talk a little bit today about the AI journey we've done at H&M. We're going to focus quite a lot on the learnings. We're going to focus a lot about what we have done the last year, created an automated solution for deployment into production. So starting out with the AI journey at H&M. But first, H&M. When I worked for small companies, I always needed to start with explaining who we were and what we were doing. Working for a large corporation like H&M, I have the luxury of not actually explaining what it is we're doing. But just to give you a little bit more insight, we're multi-branded. Many people don't actually know this, but we have multiple brands in our portfolio. So the H&M brand is just one, obviously the largest. When we talk about scale, we are at scale when it comes to our presence worldwide. I mean, we are in 72 markets, 47 markets online. I actually think we're closer to 50 now. We launched Thailand in a few weeks back. We have 177,000 employees, and we are present. I think we have 5,000 stores now. H&M has generally been very good at physical retailing. Year 2000, we had approximately 1,000 stores, and today 5,000. So our business model has been physical along the line, just opening new stores, expanding. So what is then the need for AI, having a physical retail model? I guess I don't need to tell you. But it became quite apparent around 2015. So our journey started 2015, 2016-ish, when we realized the physical business model was very hard to scale. 5,000 stores, I'm going to repeat that number over and over again. We were pretty much everywhere. I mean, the H&M business model is to locate in the high street, follow the shopping bags, and be where the customers are. But when our business model all of a sudden started growing rapidly online, I mean, our last quarterly report, 14% came from the online sales, and it's increasing quarter by quarter by, I think it's like 20%. So we see that the majority of our growth is digital. That means that our business model needs to change. That means that the way we look at data needs to change. So around 2016, our CEO initiated the first explorations about what are we doing with AI. They started a project within their business development looking on what do we do today. Because obviously it's quite hard to keep track of all different initiatives in a large corporation. And we realized then that we do quite a few things, but we don't do them centrally, and we don't do them at scale. So we are good in different markets, applying advanced analytics, but we don't see the real benefits of being this large corporation. So we initiated 2016, 7 different projects with an external consultancy firm. We initially looked at our IT landscape and where should we run this? Should we stay with the current infrastructure on-prem, long release cycles, legacy IT? And the decision was quite quickly, no. Let's go with cloud solutions. So we set up on Azure, we set up a data lake, and we let each and every one of these projects run independently on that. So Azure gave us the capability quite early to separate data from compute, which rapidly generated value. That basically means that around 2017 and 2018, most of our projects were in production. I'm not saying that they were in good production, and I'm not saying that they were covering the entire market, but at least they were generating value. They were proving that we rapidly could go from insights into production. Around 2018, we were so successful, so we were established as a function within H&M, and basically that was the first new function in 10 years. The one previous was sustainability, And if you know H&M a little bit, sustainability is a really core topic for us. So AI was promoted to be one of the big things within H&M, I would like to say. And then a year ago-ish, we started establishing this function and started looking into, so what is the next step for us? And we realized quite fast that we have proven the value. We have proven that we can get going fast. We relied a lot about using consultants for that. We want to take more ownership. So we initiated an overview and initiated a project ourselves to create more of a reference architecture around how we want to scale, how we rapidly want to go from insights into production. And just some quick facts about us. We are currently around 100, 120 people now working within this field, so in the AI functions. We are quite a diverse team, 30 plus nationalities, so we recruit from all over the world. And we use consultants, we use our HAL team, which primarily sits in our IT function, and we create joint teams. So we operate as a product organization. Basically, each and every one of our use case is set up as a product. That means we have a use case lead or a product owner. We have a team consisting of data scientists, engineers, and business analysts, all working together to deliver in that context. So the use cases we primarily focus on are covering the entire value chain. We have these ones you see here on the screen. So we do everything in the designing and buying. We have use cases in production, however, they're not governed centrally. So we try to pick up the big pieces. So these things you see here on the board are really the things we believe can deliver the most value. And when we are focused on the value delivery part, that's where we think we can get going with the rest of the organization as well. So having ended up with these use cases that you just saw, having rapidly proven our value, we realized that we are a little bit stuck. We have managed to create technical depth in our machine learning projects in just 2 years. We have a little bit of a problem when it comes overseeing these projects, because obviously if you work with external consultancy firms, they need to be managed and you need to actually review what they're doing. So what we ended up with was a very fragmented solution landscape. Having 6, 7, 8 teams running independently without any sort of governance or control. Well, obviously we had control over deliveries, but what we meant is they were so autonomous in the delivery setup in a product, they were quite free to create solutions within some guardrails. But we ended up with different solutions across the boards. This led us up to the next step. We started looking on these different processes. And basically what we realized is that the data science process or the machine learning development process is a relatively generic one. And when I say generic, it basically goes through the same stages. Obviously, there are different types of variations in this, but what we primarily can see is that there is a development phase of the model and there is a deployment phase. And then there is a layer of orchestration in between. What we also could see that when you set up projects and products without actually understanding this process, you tend to entangle the code. So you tend to treat it as a continuous process. So if you're, for instance, using an infrastructure which is quite fixed, that infrastructure will sit idle a lot of the time. Because the consumption patterns, if you look on the model development, is extremely different from the usage patterns. And also within the development phase, you will see that the training data ingestion, the data preparation, and the development will have different consumption patterns on that cluster. Some are very memory intense, some are very compute intense. If you optimize also on cost and time, it doesn't make sense to have one large, for instance, HD Insight cluster standing up there and costing lots and lots of money. So these were some of the early insights we did beginning of this year. And really what we wanted to do then is move towards a solution that easily could be transferred between different use cases. So if the process is the same, we wanted to create a reference architecture. We didn't want to create a fixed architecture because we know there are different needs for different use cases, but rather focusing on a reference, a best practice in our solution landscape. And also give reusable components, so it could be reused, not just in one, but in many. the needs are very similar over and over again. So basically, we took another look at it and tried to map out some of the very common tasks. And what you also realize in this, that if you look on data engineering, machine learning engineering, and data science, if you work with, for instance, a data scientist that a little bit of an engineer, he will try to cover a lot of these aspects. And it's very hard to find these types of skills. And usually data scientists are not the most skilled engineers. They can be very good at engineering, but usually you want very good experts and you want to create pipelines. So what we saw was that the data scientists, they worked a lot in the model exploration stage and in the model tuning stage. And if we could make it easier for them to just work in the model exploration phase, then their life would be easier. So they could focus not 10, 20% on modeling, but rather 70, 80, 90%. And given that there is a skills shortage in the market, we could get people focused on what they're actually good at. And also, if we then could create automated pipelines in the back end for these things, it would make life much easier for all of us. So the first step was basically looking into what tools do we need. And in our reference architecture that we will go through in a little bit more detail in a few minutes, we realized that if we can move our infrastructure towards more Azure Databricks, it's easier, because setting up a Jupyter notebook, handling the security, version control, is quite complex. And especially for a data scientist that's not major in computer engineering, they need to learn all the basics first. So basically, with Azure Databricks, it became much easier for them to just log into a notebook and start working with the data. And then if we then work on model implementation, we can go towards more software engineering best practices, utilizing a good code base, IDEs, and we could utilize Docker for containerization. But then also orchestrating everything with Airflow, having Azure Databricks, so the clusters, and we could start them on demand using hot pooling and things like that. So we don't need to have clusters up and running 24/7. We can start them when we need them. In some cases, there are a few minutes delay, but I mean, if you look on the costs, it's definitely worth it. And then also building a model applying or a prediction environment for different uses. So you have the offline model prediction and an online model serving. And then moving towards MLflow for model monitoring of these aspects. So it's quite interesting to follow the progress of MLflow and all the new features they're introducing, because it's very much mapped to the needs we have foreseen that we're going to have as well. So applying more principles around how we want to work is extremely important. If we can set good principles, we don't need to manage technical debt. We don't need to set up our own databases. We can use stateless, automated CI/CD pipelines, and really push for these principles being used across the board when we develop. We don't want to centrally govern extremely hard. We want to create best practices and guardrails instead. So moving from kind of a fragmented landscape into a more unified architecture will create a lot more speed. And then Keven will talk you through a little bit more on the details on how we have automated this.
Yep. Again, thank you everyone to stay so late until the end of the summit and watch our talk. I hope you will get as much as you expected from this talk. And also, I'm glad that people are not only interested with the great fashion clothes we produce from HM. My colleague Errol just shared our AI journey. Next, I'm also going to share a journey how we bring a machine learning prototype into production and scaling out to global. So a while ago, I joined a team of data scientists and machine learning engineer. Together, we solve one business problem. Of course, we start with Databricks. We write everything in notebook and do the feature engineering, data selection, model training, even model scoring there end to end. Everything went so fast. In the first few weeks, we already have a decent outcome, and the business was very happy. But on the other hand, we also realized some problem in our development process. For example, every morning we have to spend half a morning to migrate each other's notebook from previous days, and then we can split to continue development. And this is certainly not a scalable way to develop where our code base grows in the notebook. So what we did, we applied the best practices in software engineering also into this project. So first of all, we look at notebook, we take all the complex logic in notebook and create separate Python modules for them. And then in these Python modules, we expose high-level APIs for notebook. So notebook itself become very clean and not much of logic there. This also enables us to develop these Python modules locally with our favorite IDE. We can do proper unit test and refactoring locally. Afterwards, we can commit the code into Git repository. With this enable Jenkins to pick up the code and start the continuous integration loop. So for example, Jenkins can do the static code check, unit test, and then eventually package all the Python modules locally into an egg file, upload them together with notebook into Databricks, and trigger the Databricks notebook job. Then notebooks started training, and in the end, after training, log all the model information into MFlow and also model itself into model repository. This concludes the first part of the pipeline model training, and then Jenkins can start the second half of the CI pipeline, which is the building a model serving container. So Jenkins take a model from model repository based on Docker file, build a Docker image, upload into container registry. Then this enable Kubernetes to pick up the model there and do a rolling upgrade, eventually do some unit A/B tests there. So this looks very straightforward, right? However, there are lots of hiccup and the trade-off we realize along the way. Let me name a few. For example, when develop notebook in Databricks, we started with a Wang jar in the shared cluster for entire team. Then we realized that everyone have to wait a long time until other Spark job to finish, then start own kind of workload. So then we also try out why not we create one smaller but dedicated cluster per developer. Surprisingly, this not only improved efficiency, but also the cost was maintained on the same level. And then secondly, in the local implementation, these Python modules, of course, you want to hide all the complexity in these Python modules and expose high-level API for notebook. However, there is also trade-off. You want to really develop very good APIs that in the notebook, you can also examine intermediate data frames. So you can do debugging testing of, with the real data in the notebook. And then packaging. When you upload this package into the shared environment, let's say the Databricks cluster used for the continuous integration, it's important to have a good isolation between different feature branch. Otherwise, you will have a very polluted environment. So we managed to figure out a way that when upload the notebook into Databricks, we always upload into specific directory in DBFS based on the feature branch name. Then in the notebook, the first cell is always to install the corresponding egg file from DBFS, then start the actual workloads there. And thirdly, the pipeline running in the Databricks. Of course, it's very straightforward to develop all the ETL and the feature engineering code in Spark. And it's also very tempting to continue the model training in the same notebook. It works great for algorithms like random forest because it's parallelizable. But for some other algorithm, like the gradient boost tree-based algorithms, the training process is more like a sequential iterative process. It's not very easy to parallelize them. And then in this case, everything will be running on the driver node of the cluster. Even worse, if you have multiple pipelines running at the same time, they will all end up in the driver node. On the driver node, there is no proper resource management for the non-Spark workload. Then your performance will be really downgraded a lot. So we also figure out a way that to wrap this kind of non-Spark workload as a Spark job and delegate more of them into the worker nodes. That's greatly improve the efficiency. And then in the end, the monitoring part. So of course, you want to log things like hyperparameter and error metrics with MFlow. But how about something else, like input parameter, configuration parameter, git commit ID, random seed you use for the training, model itself, even the test and training data set? Do they also make sense to be tracked there? And then we managed to answer most of these questions and finish the piloting. So our business counterpart was very happy. We started rolling out and to deploy multiple, to start to train multiple models for different countries and so on. Then we start to facing some new challenge, specifically more related with this machine learning orchestration layer there. Let me name a few. Let's take a look at the data flow. So we start with a huge data set in data lake, then do the data preparation there, and then feature engineering come up with training, test, and validation data set. We do training and followed by hyperparameter tuning. In the end, we may also apply some linear optimization to come up with best business outcome. And the tools involved in this process, of course, HDFS, Hive, Spark, and NumPy, scikit-learn, matplotlib, even gRPK and Groovy for the optimization. So to conclude, The nature of these 5 steps, the first 2 steps, we are talking about really large data set with lots of parallel processing. And last 3 steps, then more become middle-level data, and we may or may not be able to apply parallel processing, partially based on the algorithm you are using, partially, for example, the hyperparameter tuning. We today use a HyperOpt specific TPE algorithm, which is a Bayesian process. It's not very easy to parallelize them either. So it's very clear that we have some discrepancy regarding the computation pattern in the entire pipeline. So first 2 steps, we are talking about distributed computation. We can leverage things like Spark. But for the last 3 steps, it's more like single computer computation. We need to leverage something else, for example, Docker container. So we do need to figure out one machine learning orchestration, be able to leverage this kind of heterogeneous computation patterns in one platform. This is the first challenge. And the second challenge, where we are scaling out, we define new concept called scenario. Each scenario represents a combination of 3-dimensional information: geographical location, for example, country, time period, and product type. Then with this one scenario, we send the whole pipeline into Databricks for the training, probably take 30 minutes. And then second scenario, take about 60 minutes. Third scenario, 5 minutes. Then we have hundreds of thousands of these different scenarios. In the end, one code base could end up training for 1,000 models, probably will take days. This is certainly not scalable. What we are really looking for is kind of task graph concept, that we have a task scenario set, and then in this scenario set we have multiple scenarios. Each of them can be broken down into 5 different tasks. Then based on the nature of task, we can either utilize a pool of Databricks clusters or a pool of Docker containers to parallelize them as much as possible to have shorter lead time of training. So to summarize, what we are really looking for is more advanced machine learning orchestration, be able to support this kind of task graph concept, and also be able to leverage different computation patterns available in Azure. Then the end goal is really about a shorter total lead time of training different models and optimize the resource usage. How to solve it? Airflow. We started with Apache Airflow partially because we have large user base in our function with Airflow, and partially because it's great functionality. Airflow has this concept of direct acyclic graph, which is very similar with our task graph concept. And also Airflow is completely written in Python, so it's very user-friendly for both of data scientists and also machine learning engineer. Airflow was initially developed by Airbnb, and then they open sourced it. Now there is a huge community back this open source project, so there is new feature keep coming. Last but not least, Airflow has lots of built-in operators which you can use to integrate with different external systems. For example, they have Databricks operator, so you can delegate a Spark task in the DAG to the Databricks cluster. And however, there's also some challenge if you want to deploy Airflow in production. For example, Airflow composes multiple components. These moving parts, each of them could be single point of failure. Secondly, Airflow, to run large workload with Airflow, you have to use either Dask or Celery, which are stationary cluster. Once set up, you cannot scaling them up and down based on your workload. And last but not least, there is great kind of dependency coupling between the Airflow infrastructure and your DAG. For example, if you want to introduce some new pip library in your DAG or in specific task, you have to do pip install not only on the Airflow server, but also on other worker nodes. How to solve this? Of course, Kubernetes, and more specifically, Azure Kubernetes service. First of all, we deploy Airflow into Kubernetes. Then Airflow web server and the scheduler become native pod or service in Kubernetes. Their availability can be more or less guaranteed by Kubernetes. And then we use Azure Postgres database to deploy Airflow MetaDB, and then Airflow for the Airflow logs and Airflow DAGs, we use Azure File Share. And then they can be injected as a persistent volume into Kubernetes service. This solves so with this kind of service, we can minimize the maintenance cost for this moving part, but their availability can be guaranteed. And how about the scalability of the DAG? Besides Celery and Dask, Airflow 1.10 also come up with this Kubernetes executor. So basically, each of the tasks in your DAG become a container, and then they can be scheduled inside the Kubernetes cluster. Even better, Azure Kubernetes Service come up with this auto-scaling functionality. So if you have lots of queuing pod which cannot be created because auto-resource, Azure Kubernetes service can automatically add new worker nodes into the cluster. Then your worker nodes your pod can be scheduled there. After all the pods finish their job and there is idling nodes in the cluster, they can be returned back into Azure node pool, which takes about 10 minutes. And then in this way, the cluster becomes very elastic. And secondly, how about this heterogeneous computation pattern? We can leverage Databricks operator from Airflow. Basically, for the first two types of tasks, we can leverage a number of Databricks clusters to run them. And then after Databricks finish the Spark workloads, they can save the intermediate data frame back into data lake. Then the following task can just pick up them and continue the pipeline. And also for the last three different Python-based kind of workload, you can also customize a Docker image used to run this kind of task. So if you want to introduce a new library, just have to create a new image and upload it into container registry. Then you don't have to do anything with Azure, the Airflow itself. There is no infrastructure impact for that. And even better, you can also customize the size of these Docker containers. So if it's a really huge scenario, you can make a bigger container dynamically. So in the end, let's take a look at the code snippets for the DAG. So it's pretty straightforward. You define a DAG with DAG ID, and then the schedule interval, like cron job. Then you can define you can first retrieve a list of Databricks clusters you can use to run this job, and then start end task. In the end, you can start to add all the scenarios into your DAG one by one. So for each of the scenario, it's kind of simplified version. You first pick up cluster, and then you can run the notebook task, which will delegate the actual Spark workload into Databricks, and then followed by a pipeline task, which will run the Python logic inside the Docker container. Here you can see how easy it is that you can specify the image and the request resource, memory, and the CPU for this task. Pretty straightforward. So to conclude, I learned two things in this journey. First of all, we should leverage the best practice in software development, also in machine learning product. For example, unit test, refactoring, continuous integration, use Docker as portable development environment, and so on. Secondly, I learned that based on the nature of your machine learning problem, your business problem, we should really think about more sophisticated architecture to be able to scaling things out, to really shorten lead time of training things. That's it. Thank you.
Thank you for the talk.
Yep.
We'll take some questions now, I guess. Sure. So, raise of hands. Yes.
Thank you. Super interesting stuff. I had a question about the model registry that you're using with MLflow from Databricks. Is that and then Jenkins needs to pull the models from out of there. Is that something external to Databricks totally, that storage, or is it within Databricks?
Today we still use MLflow as model registry, but we are not sure if it's the best choice, because we have to store the model into DBFS, which is a little bit kind of invisible. However, we can still use MLflow's REST API to retrieve the model and do the search there.
Okay, so yeah, so MLflow creates the model, it's stored in DBFS, and then Jenkins pulls it from DBFS.
Exactly.
Okay, thank you.
Any other questions?
Hi, thanks. Just expanding on that, how do you work with the CI/CD for machine learning within that? Is that within Jenkins, or you writing the unit tests outside of that? How are you fitting in CI/CD into this world when you're productionizing these models?
Yeah, basically we can make the notebook as simple as possible by put all the logic, complex logic into separate Python modules, the Py files, and then we can do proper kind of unit test locally, not only but also in CI/CD loop. Then when we commit the code into Bitbucket, Jenkins can pick up a code and start the CI pipeline, do the unit test in a more isolated environment, and also packaging, etc.
So that doesn't fit into the MLflow itself. Like, so yeah, if someone pushes a new model, a new version of the model, will you not have to write entire new unit tests, or will it fail when you try and push it? And does that cause you kind of headaches, or is it?
Yeah. I mean, today there is no kind of trigger from ML flow that you can trigger external system to start another kind of a flow to maybe when you do the commit, you only verify on one model, but when you really register in the ML flow, you want to really verify 10,000 models. Then how to trigger this? I don't see there's clear kind of indication how to do that today.
And if you look on the kind of reference architecture, having the new functionality released with MLflow, it has been part of our kind of long-term plan to also do that with the automatic rolling upgrades of models. So, I mean, we discussed early on in this year, should we develop it ourselves or should we wait for functionality to be released by MLflow? And I think we landed in, let's stick with MLflow for now and have that as a manual process. But as soon as it's now becoming more general availability, we'll start exploring if we can work with that process as well.
Any other questions?
Yeah. Second question, maybe, how do you track the how to get kind of published models across environments? Do you have is the model registry like shared between, like, let's say test and production, or are these very separate entities in Azure? How do you do that?
Yeah, actually, we create separate kind of a model registry for different environment, staging, production, development environment. So to keep a kind of isolation, so it will not happen like one accidental kind of push where overrides the production model. Yeah, that's a good point.
No more questions? Going once, going twice? Yes, one more.
Yeah, thank you. It's a really nice talk. I would like to know, let's say, when you have the set of different tasks in Airflow, so let's say if one of the tasks actually fails, so did you mark it completely failed? Because I assume that is also triggered via your Jenkins, right?
Yes.
Or
Yeah, I mean, it depends on the logic, if it makes sense. Some of the, like a branch of the logic, it's not really complete failure. I think you can also do this in the task. When you define task, you can say if it will be marked as a failure or not.
okay, so what you actually do? So do you mark it completely as a fail or just partial fail only on that one specific task?
Yeah, I mean, if it's a partial failure, makes sense, then we mark it as partial failure.
Okay, thank you.
Anybody else?
Hey, Keven, it's a great presentation. Thank you. And I have a question. Do you mind to share some experiences, or what is the challenge and opportunity for your current data science team from the data science project side?
In general, on this architecture side, I mean, if you look on how it looks today, I think some of the challenges we are facing is this amount of technical depth that we have. I mean, we have some of our data science team here, so we could ask them personally. But I mean, in my experience and when I talk to the team, it's really about, it takes a lot of time to develop new models. The amount of time they actually spend on modeling is relatively limited. The amount of time they spend on just managing infrastructure questions is too big. And that was the entire idea for us to start looking on where does data scientists fit into this workflow. So they shouldn't be all over the map. And today they are a little bit all over the map. They work with some engineering questions, there's a lot of maintenance, a lot of production. We want to extract them from that. We want that to be engineering topics. So, I mean, that is a part of their environment, and I guess that's true for many of the companies. And we want to enable this. And we think, I mean, putting Databricks up here, being here speaking, is really about, we think Databricks is the solution for us, giving them a better environment to work in.
Okay, thank you.
Any other questions? Okay, in that case, let's thank the speakers one more time.